Hi everybody. I had a few questions and I looked on the discussion board and saw several of you are having problems with this problem on your homework assignment. So I wanted to go over this with you. So here's the first question. For a data set of chest sizes, distance around chest in inches, and weights of 4 anesthetized bears that were measured, the linear correlation coefficient is R equals 0.563. Use the table available below to find the critical values of R based on a comparison of the linear correlation coefficient R and the critical values. What do you conclude about a linear correlation? So here's what we do. First of all, if you click on the icon, you can open up the critical values for R. So I look back in the problem and I see that I was told I have 4 anesthetized bears. So to show that there's linear correlation, the critical values are going to be plus or minus 0.950. So I'm looking in this column at the number of measurements I have, and then I'm looking at the corresponding critical value. It's plus or minus because they could be negatively corresponding or negatively correlated. If the R value is negative and positive, it's positive. So the critical values are plus or minus 0.950. All right, and then the next question asks you to make a conclusion about this. Since the correlation coefficient, now the correlation coefficient we were given is 0.563. Since that is going to be between positive, or I should start with the negative. Since that value is between negative 0.950 and positive 0.950, so it's between the critical values, there is not sufficient evidence to support the claim of linear correlation. There's going to be linear correlation if the critical value we're given here is either bigger than positive 0.950 or smaller than negative 0.950. So there is not sufficient evidence for this. Okay. I also heard questions about this question. So for a data set of brain volumes and IQ scores of 7 males, the linear correlation coefficient is found and the p-value is 0.691. Now a p-value is different. A p-value is not the same as R, the linear correlation coefficient. So what we're going to do is write a statement that interprets the p-value. So this p-value is 0.691. So that means the p-value indicates that the probability of a linear correlation coefficient that is at least as extreme is 69.1%, which is high. That's very high. And since that is very high, there is not enough sufficient evidence to conclude that there is a linear correlation between brain volume and IQ scores. So rule of thumb is the p-value has to be pretty darn small, like 0.05 or smaller, to indicate that there is sufficient evidence to conclude that there is a linear correlation between brain volume and IQ scores in males. I encourage you to look on page 71 and 72 in your textbook. So I'm going to pause this for a second and pull that up. Okay, so this is page 71 in your textbook, and you can see the definition of the p-value. If there really is no linear correlation between two variables, the p-value is the probability of getting paired sample data with a linear correlation coefficient R that is at least extreme as the one obtained from the paired sample data. Okay, so that's like the probability that you make a mistake and say there's linear correlation when there isn't. The next page of the text written here real in bold helps you and really is what you should have been looking at to answer the question from your text, from your homework assignment. Only a small p-value, such as 0.05 or less, or a 5% chance or less, suggests that the sample results are not likely to occur by chance when there is no linear correlation. So you assume, because you're looking at your R coefficient, their linear correlation coefficient R, and you see you got 0.99. So this is saying, well, this is the chance that that was a mistake. So it's got to be pretty darn small for you to conclude that. So anyway, I hope that helps.